Section 4.4, Laws of Logarithms. Okay, remember that a logarithm is not an operational symbol. It's not like addition, subtraction, division, multiplication. It's not that. It's a function. It's a function that is described by the simple process of looking up the table of an exponential function and reading it in reverse. Right? That's all we're doing with the log. So when you see log, when we see log, why does this always jump to the most thick bar? Okay, so when we see something that says log base 2 of 8, we know that this is saying, okay, go to the table that has 2 to the power of x, right? And we got to read this in reverse. We got to find where 8 is on that table and read it in reverse this way. 2 to what power equals to 8? And if you know your powers of 2, then that's how you'll know that the answer is 3, right? The answer is 3. And that's because 2 to the power of 3 is 8. Okay, so for that reason, whoa, how did we get to this? That's cool. I don't know how I jumped way down there. But anyway, for that reason, there are special properties of logs. It's not an operational symbol, so therefore multiplication, just like multiplication, division, addition, subtraction, those are operational symbols. And properties, say like distribution, exponents, the rules of what we're allowed to do with operational symbols differ from logarithms, right? Logarithm is a function and it has its own special properties. So we're going to look at those properties. Okay. Okay. So laws of logarithms. Here they are. Right. So here are some of the most common ones that we're going to use, and I'm not going to go through the proof of them, why they're true. Let's zoom in a little bit more. But let's just describe what they're saying. This is saying that if we have a multiplication of two values, a times b, inside the argument of a log base a, then we can separate this as the summation of two logs. So for property a, this is saying that we could have log base 2 of a multiplication, like let's say it's 3x, right? That's a multiplication. And according to property 1, this is equal to log base 2 of 3 plus log base 2 of x, right? So we can separate this multiplication in here. Multiplication inside the argument of the log can be rewritten as the summation of two logs with the same base, right? We keep that same base in the index of the log. Good. Same thing happens. A similar thing happens with division. If we have log base a of a division of two values, a over b, then that's equivalent to the difference of two logs with the same index of the log. Right? So again, just as a quick little example, if we have log base 2 of some division, maybe that division is x over 3, so there's a division in there. According to this property, this is equivalent to log base 2 of x minus log base 2 of 3. Right? So again, we have a division in here, a division inside the argument of the log, can be rewritten as a subtraction, a difference of two different logs with the same index and in this order. The value in the numerator of this fraction goes here, the value in the denominator of the fraction goes there. But again, I didn't really prove why that is, but we're just going to use these properties. Good. And then last and probably most important is this one. This is saying that if we have a value written in exponential notation inside the argument of the log, then we can take that power and move it out in front like a linear factor times log base a, so we keep the same index of the exponential number, we write it to the power of 1. So, for example, if this was log base 2 of 8, we can rewrite this as, well, okay, we know that the answer is 3, right? Log base 2 of 8 is 3. Okay, so we can rewrite log base 2 of 8, we can rewrite it as log base 2 of 2 to the third power, right? Because 8 equals 2 to the third power. And according to this property, since this is written in exponential notation, we can take that out in front and write it as a linear factor. So we can rewrite this as 3 times log base 2 of 2. Log base 2 of 2 is 1, so we know that 3 times 1 is 3, so we're going to get the same answer. Right? And that's true no matter what exponential value is in here. It just so happens, just for the purposes of this example, I made this index and this base match, but they don't have to. According to that property, if I have log base 3 of 5 to the x power, then that property says I can take this exponent here, move it out in front like a linear factor, and rewrite this thing as x times log base 3 of 5. Log base 3 of 5. So this is a really important property because it allows us to solve for whatever exponent is in there. And so we get to rewrite it as something that does not involve an exponential power. We'll see how that's useful in the next section. But it is a really important property of logs. Okay, remember log is a function, so we have to be careful about the rules we're allowed to use. So use these rules and be careful not to kind of create your own rules. It's very tempting to want to say that things work differently. So for example here, this is the rule. But very often people confuse this. They see log base 3x, and they see that there's multiplication in here. So they think that this is equal to log base 3 times log base x. Right? And that's not true. When we have a multiplication in there, then that turns into addition of two logs, not this way. That's not true. Right? Another common mistake is that people think this works backwards. So if they see log of 3 plus x, maybe it goes backwards, and it equals to log of 3 times log of x. That's not true. And also they maybe kind of think that there's some sort of distribution process that happens. So this one's also not true. And then the last, or another common mistake is that people think this is true, that we can somehow distribute this log and end up with log of 3 plus log of x. Some sort of a distribution process here. And again, that's also not true. Right? There is no property that says that you're allowed to distribute a log across an addition like this. So none of these are true. We have to be very careful about what we are allowed to use, right? And that's what this table gives us. 3 properties that are true. If there is multiplication inside the log, it's equal to an addition of 2 logs. Now you can go backwards from here to there, or forwards, right? The summation of 2 different logs with the same index equals that. But you can't have an addition inside the argument of 1 log and somehow separate it into, something like this. This is not true. Good? Any questions? Okay, so let's evaluate some of these things. Of course, if we had a calculator, we could do it. This is saying 4 to what power equals to 2. 4 to what power equals to 2, so I think we can kind of guess what that is. And then also this one, 4 to what power equals to 32. So, okay, we can kind of get a sense of what that is saying. But instead, we're going to try and use these properties to combine it as one single happy log, and then from that, get our answer. Okay, so they have these two have the same index, so that's going to be like property number 1, this one, the summation of 2 logs with the same index, and that's equal to 1 happy log with the same index, and then we multiply the arguments of these 2 logs. Okay, so this is going to be equal to this. This is equal to log base 4, we keep the same index, of 2 times 32. Which will be equal to log base 4 of 64. Right? And then when I want to find this answer, I got to think to myself, 4 to what power? Remember this little thing. 4 to whatever this answer is, the answer there, 4 to the power of that must be equal to 64. Right? So what is that? 4 times 4 is 16. 16 times 4 is 64, so that's got to be a 3. Good. Questions? And this is because 4 to the power of 3 equals 64. Good. Same with the difference of 2 logs with the same index. According to property 2, if we have a subtraction of 2 logs, then that's equivalent to 1 log with a division of these 2 arguments in this order, and we keep the same index, a in that case. Okay, so in this case, it's base 2. This is going to be the same thing as 1 big happy log, base 2, of 80 divided by 5. Good. Questions? Okay, so this is going to be equal to log base 2 of 80 divided by 5 is 16. And so now when I want to find the answer to this, again, I think to myself, 2 to what power equals to 16? So 3, 4, right? That works. And that's because 2 to the 4th power is 16. Questions? No. Okay, this last one, how do we simplify this? Well, we can use the cube root of this thing to get us to a 2. There isn't going to be a simple, happy little answer, but I think maybe we can just approximate it with a calculator. That's probably the intention here. So we can just use our properties to rewrite this a little bit. According to our third property, we can write the third property. If we have a constant out here, we can rewrite it as a log with this value in the argument of the function raised to the power of this constant out here. So, according to that property, this is the same thing as log of 8 to the power of negative 1/3. Good. And negative 1/3, well, that's the same thing as log of 1 over 8 to the positive 1/3 power. And we know that that's the same thing as log of 1 over the cube root of 8. So that'll be log of 1/2. Good. Okay, so even though I don't really know the answer, I know at least what it's asking me. Right? By default, if there's nothing here, there's nothing written here, that means there's a little 10. Right? And whatever this answer is, it'll be 10 to whatever that power is, must be equal to 1/2. 10 to what power equals to 1/2? That's what they're asking us. Good. Okay, well, luckily 10, log base 10 is a nice, pretty number on our calculators, so we can just go over our calculators if you ever get stumped with one of these. So let's launch our calculator. So log of 0.5 equals this decimal, right? And that works because that must mean that 10 raised to the power of that decimal, negative 0.3010, let's just approximate it to 3. Pretty close to 1/2. Good. Any questions? No. Okay, let's see what the author did for that last one. Okay, so we had that this must be 3. We got that one. And, okay, same thing. So they used the calculator. So we can just stop at this point and go, okay, I've simplified it as far as I can go, log of 1/2. Or if you have a calculator and you want to round it to some decimal value, you can just use technology at that point. Any questions? No? No. Okay, expanding and combining logarithmic expressions. So we can use these properties to either expand or combine logarithmic expressions, and that can in turn help us solve logarithmic and exponential equations, which we'll do in a little bit. But first, we want to take baby steps and learn how to use these properties to both expand and contract these functions. So use the law of logarithms to expand these expressions. So you want to go in one direction to expand them. So here for this first one, we have multiplication. And we know that if we have a multiplication inside the argument of a log function, that means that we can rewrite it as an addition, right? So for a here, we're going to have that this is equal to log base 2 of 6x is equal to log base 2 of 6 plus log base 2 of x. Good. Any questions? For b, we have log base 5 of x to the 3rd power times y to the 6th power. So first, we have a multiplication, so we can separate that as the addition of two logs. So this would be log base 5 of x to the 3rd power plus log base 5 of y to the 6th power. And next, we can use our third property to bring that exponent out in front like a linear factor. And so this becomes 3 times log base 5 of x plus 6 times log base 5 of y. Good. Questions? The third one, C, we have ln of AB divided by the cube root of C. And remember, ln is just log base E, so all the same properties apply. we have a giant division here, so this is going to be ln of AB minus ln of cube root of C. Cube root of C is the same thing as C raised to the power of 1/3. So this can be separated as ln of A plus ln of B, right? Because here's a multiplication, minus ln of C to the 1/3 power. And then we can bring that 1/3 power out in front and rewrite this as ln of A plus ln of B minus 1/3 ln of C. Any questions? No? No? Okay, let's see, that matches what we got. Here's what your author did. Law 1, and then law 3, and then same thing we got. So the logarithms can also serve us to, in the process of expanding, that was done in example 2, that is, we can write sums and differences of logarithms as a single logarithm. So combining logarithms, we can go backwards. So given a long expanded expression like this one, we can use the properties of logs to combine the whole thing into one big happy log. So for part A, let's put it here, log A, part A, we can say that we have log base 10, log base 10, they have the same index. By the way, if they didn't have the same index, things would be a lot more complicated. So if this was log base 3 and this was log base 5, things would get tricky. So we'd have to do some other work. We can't just apply this, this property straightforward. So luckily for us, they're both log base 10, right? By default, if there's nothing there, they're both log base 10. They have the same index. And there's an addition here. So we know by property 1 that this must be equivalent to one big happy log. Wait a minute, that property though applies to the summation of two logs. Notice that there is no constant out in front. So let's go back over here. Where's that property? Oh, here. Notice that when we apply this property, there is no there's a constant of 1 out in front of log base A of A and a 1 in front of log base A of B. So if there's something in front there, we're going to have to use property 3 first to rewrite it like this and then go backwards. Right? Okay, let me illustrate what I mean by that. So a common mistake is to take this and, here, let me just copy it over here. We have 3 log of x plus 1/2 log of x plus 1. Okay, since we see addition, people usually notice that that must mean some sort of multiplication of the two. So that, oops, I put an L in there. Log of this. Okay, so it's got to be log of something multiplied by something, right? Something multiplied by something. And it should be this something times that something, but what about the 3 and the 1/2, right? How does that work into this whole process? So before you jump into this, we're going to have to rewrite this without those coefficients out front. And we do that by using property 3. We're going to take these guys and move them from here and into the exponent of there. Good? Okay, so we're going to first rewrite this as log of x to the 3rd power plus log of, and now you got to be careful because it's the entire thing raised to the 1/2 power, not just the 1, not just the x, but it's x plus 1 raised to the power of 1/2. Okay. Now we're ready to rewrite this as one big happy log, log of, and it's x to the 3rd power times x plus 1 to the 1/2 power. Any questions? Questions? No. Okay, looking at B, let's move this down here. B, we want to do the same thing. We have 3 ln s plus 1/2 ln t minus 4 ln t squared plus 1. So we want to take all these exponents, and all these constants, coefficients out in front, and move them into the exponents. And then we'll be able to deal with the addition and subtraction properties. Good. So then this is equivalent to ln of s to the power of 3 plus ln of t to the power of 1/2 minus ln of t squared plus 1 raised to the power of 4. Good. And now these two, because we have an addition, combine into ln of 5 to the 3rd power times t to the 1/2 power minus ln of t squared plus 1 raised to the 4th power. And now we have a subtraction, so these two divide. And so my final result for b equals that, and so my final result will be ln of 5 to the third power times t to the 1/2 power all over t squared plus 1 to the 4th power. So that's pretty good, but you might want to expand this, right? So the rule of thumb here, the guideline is that if this exponential number turns out to be a number less than 1,000, we usually like to see it expanded, otherwise leave it as an exponential. So you might find this final solution to be 125. Also, fractional exponents, if it's a simple one like a half or a fourth or a third, people usually like to see it as a root notation. But if it's a different one or more complicated, we like to leave it in a fractional exponent. So it's pretty common to see this way. 125 square root of t all over, and then this one we definitely don't want to expand, right? So t squared plus 1 to the 4th power is pretty ugly, so we leave it alone. Any questions? No? We're good? Expanding and contracting using our properties? Expanding and combining. Okay, so we did that one, we got that, and we got that, right? So author got the same thing. Okay, so we can use these properties in various applications. So here's one application of logs. In social sciences, we try and come up with a model that describes how long it takes people to forget information. So if a task is learned at a performance level P0, right, then after a time interval T, the performance level P satisfies this equation. Okay, so P0 is some sort of metric to gauge how well you understood a given task. T represents time. C represents some constant that is special to that task. And then P is your performance level after T time has gone by. Okay, so part A says solve for P. So let's first of all just use our awesome properties to solve for P for part A. We have log of P equals to log of P0 minus C log of T plus 1. Okay, what I want to do is combine these two into one big happy log, since they're all log base 10. Right? We're trying to solve for P. Remember, I can't just, this is a very common mistake. You go, okay, solve for P, people do this. Log cancels, and log cancels, right? That's not true. There's nothing in the properties of logs that say that you can divide by log. That doesn't make any sense at all. That's kind of like saying, if I have square root of x equals to 1 plus square root of, 8, that somebody comes in and says, I know how to solve for x. I'm going to divide by square root, divide by square root, divide by square root. I'm like, what in the world is that, right? This notation is meaningless. This function needs an input, and that's the same as this. Just dividing by log is meaningless. You might accidentally get to the right answer. That happens sometimes, but that doesn't mean it makes any sense. Good? Okay, so we don't want to do this. Any questions about this at all? Right? Okay, so we don't want to divide by nonsense. That doesn't make sense. Okay, so what are we going to do? Let's combine these things into one big happy log. Oops. Let's go back here. So we have log of P equals to log of, and this is going to be a division, right, because of the subtraction. And then what I'm going to have to do is take this exponent and this constant and raise it into the exponent of that guy. So I'll end up with P0, and then here we end up with T plus 1 raised to the power of C. Good. Okay, now we can say that P must be equal to this, right? Because we have log of this equals log of this, so therefore these two things must be equal to each other. Good? Questions, questions, questions? Like if I have the square root of, x plus 1 equals the square root of 25, then I can conclude that x plus 5 must be equal to 25. Good. Or the other way you can think of this is that we can raise both this way. We can say that this is 10 to the power of log P. So we apply this into the function, to the function 10 to the x power, and we do the same thing to the other side, 10 to the power of log of this, P0 over T plus 1 to the power of C, right? Either way, these two operations undo each other, and we end up with the statement that p must be equal to this, t plus 1 to the c power. Okay. Any questions about this? No? We're okay with it? Good? Okay, so if we're trying to solve for something, and it's kind of buried inside a log function, and we can simplify it and get it to a point where log of something equals to log of something, they're the same index, the same index of the logs, then those two arguments inside those logs must be equal to each other. Right? So that's a general rule that we have. Log base a of x equals log base a of y. Right? If this is true, log base a of x equals log base a of y, then we can conclude that x must be equal to y. Good. This also applies to, for example, if 2 to the power of x is equal to 2 to the power of y, if they both equal each other, then we can conclude that x must be equal to y. Good, good. Okay, so part A said solve for p, we did that. Going back to this word problem. We have this weird function here, this weird expression that expresses the relationship between how long it takes for you, the retention of knowledge over time. Right, so then part B says apply it. We have, if your score on a history exam is a 90, so that's your initial level of performance on this history test, that would be P naught. So we're saying P naught equals to 90. What score would you expect to get on a similar test after 2 months, and then maybe after a year, assuming that the constant coefficient value for this type of a task is at 0.2? Right? Okay, so the values are all given. This is saying P naught, from here we get that P naught must be equal to 90, and C equals to 0.2. And we want to know what's going to happen for different t values. We have t equals to 2 months, and also t equals to 1 year, so t also equal to 12 months. So that's what we want to know, right? And then p is the question mark. So we solved for p, so all we have to do is plug and chug now. So for t equals to 2, then we have that t equals to p naught, which was 90, over t, which is a 2, plus 1 to the power of 0.2. And this will give me my answer. And for t equals to 12, that's not a 12, then p equals to 90 divided by 2 plus 12, 12 plus 1, I should say, to the power of 0.2, and this will give me my answer. Okay, so this is going to be 90 divided by 3 to the power of 0.2, and this is going to be 90 divided by 13 to the power of 0.2. Okay, we can use our calculator and get an answer from there. Let's just see what the answer is over here. Okay, so they got the same result as I did for solving for p. Now when you plug it in, you get these. After 2 months, t equals to 2. That's 90 over 2 plus 1 raised to the power of 0.2. So after 2 months, you would expect that your score should be around 72. And after 1 year, your score should be somewhere around 54. Right? If you don't use it, you lose it. So even though you had learned this material up to a proficiency of about 90, after a year of not working on this, not thinking about this, if you were given a similar exam, your score is expected, according to this model, to be in the neighborhood of 54. Good. Any questions? No? Okay, so you might have noticed that so far in our calculator there were only 2 easy buttons. There was a button that had ln, and there was a button that had log. Right? So this one by default is base 10, and this one is base e. But what about everything else? What if I wanted to find log base 7 of, I don't know, 13? What is it saying? This is a decimal, so that 7 to the power of that decimal equals to 13. How do I find that on my calculator? Now, some of you guys do have a button on your calculator that lets you type in this exact thing right here. It lets you type in the index of the log. So I'll show you where that is in a second. But for you guys, when you see that button, it'll do this, and then it'll be a little blinking box right in there. And then you can stick in a 7 right in there, and then stick in the 13 right in there, and then that'll give you your answer, and you're good to go. But what about everybody else? What if we only have these 2 buttons? Well, luckily, it actually doesn't really matter very much. There's an easy way for you to change the base of any log function, and that's with this knowledge. So let's say that you're asked to find this. What is y when it equals to log base b of x? And let's say b is not a common function, log base 7, right? So this one's saying, what is log base 7 of x? What is log base 9? And that might not be a button on our calculator, right? Okay, so by definition, oops. By definition, remember this must mean that b to the y power equals to x. Usually I see it written, usually we've had it written in the other direction. So let me just flip it around. Right? So by definition, this must mean that this raised to that power equals to this, right? That's what we've been working with. So that must mean, by definition, that b raised to the y power must be equal to x. Okay, remember, we're trying to solve for y. We want to know what y is. All right, so now what we can do is we can apply a log to both functions as long as it's the same log. And we can apply whatever log we want. So let's say we apply log base a to this side, b to the y, and we apply log base a to the other side. Right? We're maintaining that equality. We're applying the log to both sides, the same index, and a is anything you want, any real number, real number. Good. Okay, so now we have our properties of exponents. We can move this guy out in front and rewrite it as y times, and then we have log base a of b must be equal to log base a of x. And finally, we can divide both sides and say that y is equal to log base a of x divided by log base a of b. Good? Good? Questions? Okay, so here is the exact same thing. We have that b to the y power, right? This comes from the statement that y equals to log base b, log base b of x. So b to the y power equals to x. Apply a log base a to both sides. Move the exponent out in front. And so we get this. Okay, how is this important? Okay, so for example, let's say that I wanted to find out what is log base 7 of 13. What in the world is that? I know conceptually it must mean that it's the answer to this thing. And we use the variable x way too much, so I don't know if it helps for me to do a happy face. The answer is happy face, right? And what's special about happy face? Well, happy face is the number. It's a decimal number, such that 7 to the power of that decimal, 7 to the power of happy face, must be equal to 13. Okay. All right. Well, I can take logs to both sides, log base anything. So I can apply log base there, 7 there equals to log there. And here we have log happy face. Okay, so we can apply log base anything, log base 2 to both sides. That's fine. We can also apply log base 19 to both sides. Nothing special there. We could do that. But as long as I get to apply any log I want, why not pick a log that is easy to work with? So base 10, or just leaving it as log, is easy to work with because my calculator has a log base 10 button, right? Or the other popular one is log base e. So I can apply log base e to both sides, otherwise known as ln to both sides. And then it'll be an easy button on my calculator, right? So let me just leave it as log base 10, which means I don't put anything there at all, just log. And then I can move that exponent out in front, right? That's one of our properties of logs. So then this would be saying that that happy face would be times ln, oops, not ln, times log of 7 equals log of 13. And just so people don't forget, and we're still getting used to this, I'm just going to go ahead and write the 10. Log base 10, log base 10, log base 10. Okay, and now we divide both sides, and we get that this happy face, the answer that we were looking for, is equal to log base 10 of 13 divided by log base 10 of 7. Okay, we wouldn't want to have to do this work every single time. It's a very simple pattern that we notice. If we are asked to do a log of some index that is not a common one, not a 10 or not an e, then what we could do is change it to whatever base we want, something convenient like 10 or e, and then what we do is we create a division where the numerator is log of the index we were interested in divided by log of the base we didn't want to work with. Good? Maybe? Sort of? Common? No. Okay, so let's use our calculator to find this answer, just to confirm. So, launch calculator. So if we have log base 10, that's just going to be the log button. Let's get rid of this thing. Clear. Okay, so log of 10. Oops, not log of 10. Log of 13 is this. Remember, what is that decimal? This means that 10 raised to this decimal equals to 13. We can confirm it. 10 to the power of 1.1139, we'll stop there, is approximately 13. Pretty close, right? And then log of 7 is equal to this decimal. This must mean that 10 raised to the power of this decimal, 0.845098, approximately, will be pretty close to 7. Okay, so we have an answer to both of these two. Let's move it over here. And then we can scoot this guy over here for now. Okay, so from our calculator, we can see that this numerator is going to be the decimal 1.1139394332 divided by log base 10 of 7, which is this decimal, 0.845098, right? These two decimals. And now if I figure out what is the division of those two ugly decimals, let's just use our calculator over here. So then this is equal to 1.1139433352 divided by 0.845098. It gives us that decimal. So from our calculator work, we can get that this division of these two things is equal to 1.318123, approximately. Okay, let's step back and see what we just found. This might have confused some people. Okay, so we started with this up here. We wanted to know, what is this? What is log base 7 of 13? Conceptually, I should know that the answer to this happy face, the answer to this should be some decimal so that 7 to the power of that decimal equals to 13. And that's what this is saying. Good. So to confirm that it works out, it should be true that 7 to the power of 1.318123 should be pretty close to 13 if we did a good job. Right? So we can confirm it works. By saying that 7 raised to the power of 1.318123 approximately should be pretty close to 13, and so it worked out. Good. Any questions about that? No? Okay, so let's do one more example where we don't do all that work. Right? So what this is saying is if we have, the question is find, if the question is, find log base, 13 of 52. 13 to what power equals to 52? That's what they're asking you to find out. You can go, well, I don't know, my calculator doesn't have an easy button for 13, log base 13, but luckily, thanks to this change of base function, we can change it around and say that log base 13 of 52 is the same thing as a division of, and then I can use any log I want. I don't want to work with 13. Let's say I want to work with ln of 52. But then you have to divide it by ln of the index here. The log that you didn't want to work with was 13, so you have to divide it by ln of 13. the division of these two will be equivalent to the answer to that one. Okay, so we go over to our calculator. I'm just going to do it on my calculator over here. So this would be ln of 52. This gives me 3.9512 approximately, just to speed things up. And then ln of 13 gives me 2.5649. Right? And why is this true? This must be true because e raised to the power of this decimal equals 13. And e raised to the power of this decimal equals 52. So this is not the answer to our question. This is not the answer to our question, but the division of the two will be the answer to our question. So when we divide these two, approximately we get 3.9512 divided by 2.5649. We get approximately 1.54049, approximately. And so now that becomes our answer. Right? This is our answer to this. That's what we originally wanted to know, 1.54049. And we can check. We're just getting check by noting that 13 to the power of 1.54049 is pretty close to 52. 13 to the power of 1.54049. Yep, pretty close to 52. Any questions? No? Okay, so here's our table indicating the change of base formula. Log base b of x equals to log base a of x divided by log base a of b, where the value of a is any real number that's positive, right? Logs have to have a positive index not equal to 1, or if it's equal to 1, it kind of becomes an obvious one. Good. Okay, so here's a couple really quick ones we can solve. Log base a to 5. Well, if I don't have an easy button to figure out index of 8 in my calculator, then I can say that this one, log base 8 of 5, let's use log base 10. Since that's a nice easy button on my calculator, is log base 10 of 5 divided by log base 10 of 8. Right, so those just become nice easy buttons on my calculator. So I can hit log of 5 equals to 0.69897 divided by, and then log of 8, so log base 10 of 8 is 0.90309 approximately. And then when I divide these two, I get 0.69897 divided by 0.90309. It's approximately 0.773976-ish, right? And we can check to see if it's true, if it all works out. It must be true that 8 to the power of 0.773976 is pretty close to a 5. Good. 7739, is that what the author got? 7739. Good. And they also use log base 10. We could just as easily have used log base e. Nothing special about log base 10. So just for the sake of making sure that works, we can have also said, let's try saying that this is equal to ln of 5 divided by ln of 8. Right? We can change it to any log we want, and ln of 5 equals to 1.6094 divided by ln of 8 equals to 2.07944. Remember, this is the decimal such that e raised to this decimal equals to 8. E raised to this decimal equals to 5. Notice that this right here does not match this, and this does not match that. However, this division will be equivalent to that division. The result of those two will be equivalent, approximately, right? Off by a little bit. And so we'll get the same answer. Any questions? No? 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 And so log base 9 of 20, let's just look at the answer to that one. Log base 9 of 20 is ln of 20 divided by ln of 9. And we can just use our calculator, divide these two, and we get approximately this decimal. Try it on your own. And that must be true, right? If we check, it must be true that 9 to the power of 1.36342 is approximately 20.